We've been completing the square for a while now, and that is taking a quadratic expression like this and writing it as a perfect square plus or minus a constant term. And there's been a lot of questions about how to handle situations like this, where we have a leading term, our x squared term, has a coefficient that is not equal to 1, and like this example that we have from one of our slides. And I'm just gonna go back and do kind of a simpler problem here real quick. Um, here's a pretty simple challenge to complete the square for this particular quadratic expression. And I'll just remind you that what I do is I take the x squared uh, in my area model. That's represented by this square that has dimensions x by x. And so thus it has area x squared. And notice this is a perfect square already. And that's important. This term right here is a perfect square, which is why I'm able to take the rest of these pieces and build a bigger perfect square. And that's what I do. I take this 6x and I put 3 of those 6x's over here, and I put 3 of the 6x's down here. This is 3x and 3x. And there's my x squared and my 6x's together, and you can see the dimensions of our bigger perfect square are starting to materialize. This is going to be x plus 3 squared, as long as I can figure out how to get 9 units in that corner. And of course, we don't have 9 units. We just have 4 units. And I can't just change my 4 to a 9. This is a totally different expression than the one that I started with. So in order to get back to the original expression, I have to subtract off 5 of those units. And now you see this expression that I've written here is equivalent to this one. And so when I also like to think about taking this constant term and splitting it between these two constant terms, so that I have one that completes the square and the other one that balances out my expression so that it's equal to the original expression. And then it's easy. I just factor, and I'm finished. I have a completed square. And again, the main point here that I'm trying to make is that it's easy to complete this square because this thing is a perfect square. And so over here with this problem, we have 2 x squareds, which looks like this. We've got an x squared plus an x squared. And so this rectangle has dimensions 2x by x. There's no way to divide these other bits up in order to turn this thing into a perfect square. And so my suggestion was to factor out the 2. And when you do that, you end up with a decimal number, and we can handle that. So notice now I've got a 2 factored out, but I'm going to focus my energy on completing the square that appears, that's for the quadratic that appears inside this parentheses. And notice it's actually going to be the same perfect square that we have over here. I know that this 6.5 needs to be a 9 in order for this thing to be a perfect square. And I can't just change it to a 9, so I basically add 2.5 to it to get 9, and then I just subtract off that 2.5. And now I can complete this square right here. This is the perfect square, so I'm introducing this bracket instead of a parentheses, because I want to use my parentheses here inside to contain my perfect square, and then I have a minus 2.5. And there, I was easily able to do that. And now I'm going to distribute the 2 back through this expression and just clean it up a little bit. 2x plus 3 squared minus 5, because of the distributive property. And that is the completed square. That's how we complete the square when in this case we have a leading coefficient of 2. But I was working on this with some students, and we figured out another solution that maybe is a little more elegant, or maybe you like it a little bit better, but either way, it's going to give us a little more insight into how to handle this problem. 2x squared plus 12x plus 13. So now imagine, I'm going to go back to my area model and draw my 2x squareds right here. There they are. And I know this is 2x. And remember, this is not a perfect square. So if I don't have a perfect square up here in this corner, I can't really move forward. So what if I just doubled the number of x squareds that I had? And now I have 4x squared. And that is a perfect square. It's 2x by 2x. But of course, you can't just double something out of convenience. So instead, what I'm going to do is I'm going to take my expression, and I'm going to multiply it by 2, plus 24x, plus 26. There it is. And then I'm just going to divide it by 2. So I'm being clever with the multiplicative identity, right? I multiply by 2 and then I divide by 2. That's the same as just multiplying by 1, which is totally okay to do that to an expression. We have something here that is an equivalent expression to the one I started with. So again, now I'm going to focus on completing this square. And I got the beginning of it, 4x squareds. Now I'll take these 24x's and I'll put 12 of them right here. That looks like this. I gotta double them up so that I can fill up this entire space right here. And I'm gonna put another 12 down here. These are 12 x's. Each of these is like an x times 1. So there's 1, 2, 3, 4, 5, 6 times 2 of them. There's 12 x's here. And this dimension becomes 6. And also this is 12 x's. And so this dimension becomes 2x plus 6. And now you see the beginning of our square. And notice that in this corner, 6 times 6, we need 36 units in order to complete this square. So let me take my expression again, 4x squared plus 24x plus 36. And then I'm going to subtract off 10 to get back to the original 26. And I'm still dividing this whole thing by 2. So that's interesting. Now we've got a perfect square and a constant term inside. So let's take a look at that. It's 2x plus 6 squared minus 10, all divided by 2. And maybe you could see that there's some similarities here. And a lot of students might go and just divide this thing by 2, divide this inside the parentheses by this 2, and just get x plus 3 squared. But that's not really allowed because it violates our order of operations. We have to evaluate the exponent before we're allowed to do any of that division. So let me take a closer look at this. 2x plus 6 squared is 2x plus 6 times 2x plus 6. And then I'm going to subtract 10 and divide by 2, just retaining the expression completely. And now look, I could factor a 2. Actually, I can factor a 2 out of each of these things. So let me do that. 2 times x plus 3 times 2 times x plus 3 minus 10, all divided by 2. So if I divide this thing by 2 right here, then one of those 2's is going to divide out, and I'll retain one of them. So this becomes 2 times x plus 3 squared. And then if I divide my negative 10 by 2, I get negative 5. And there you go. I've got the same answer here that I got the first time that I did it. So there's a couple of different approaches for completing the square with this leading coefficient other than 1.